State University.
And my name is Nathan Hertz, and I'm also an electrical engineer, junior year here at Utah State University.
And this is our final project for ECE 3710, microcontrollers.
Our microcontrollers project consists of a device that uses a Wii Nunchuck as input to control a robot that draws in sand.
This project meets up the criteria proposed in the project because it has an input, which is the analog joystick on the Wii Nunchuck, and outputs, which are 2 stepper motors to control the project and move it around. We were able to meet all the requirements we listed in our proposal. We had a nunchuck that was fully able to control our outputs, and both our motors were able to work independently of each other. The requirement that we want to have is that our 2 motors were able to move 2 independent axes, an X and a Y axis, that was able to give us a full range of movement around our sandbox.
The dependencies for our project include power sources, a 3.3 volt power source to power our microcontroller, and as well as a 12 volt power source, 12 volt 2 amp power source to power our motors. We also had a dependency about our communication protocol with the nunchuck. It requires I2C communication to communicate with the microcontroller to send the analog joystick values. As well, the last 2 dependencies that we needed were stepper motor controllers to communicate with our stepper motors and the microcontroller. We were able to acquire 2 of these to better help communicate to these 2 motors to make the programming as well as the implementation into our project a lot easier.
So this is the physical circuit for our project. For the power supplies, we have first the 3.3 volt going into the positive terminal on the left side, and on the other side we have a 12 volt power supply that goes into the other power terminal on the right side. The left side power terminal goes to both of these motor drivers, powered into their VDD port, flowing that way. Both motor drivers are then connected directly to the motors using 4 pins that control the A1, A2, B1, and B2 pins on the motors. Both these drivers also have the 12 volt power supply going into them on their V mode pin, and this power is then sent directly to the motors. And using this potentiometer, you are able to adjust the power in amps going to the motors. Finally, there's the nunchuck interface, which just plugs directly in. This nunchuck interface is also powered by the 3.3 volt side, and it has 2 pins, the clock and digital communication, that go directly to the microcontroller. Both the motor drivers are also controlled by the microcontroller using a step and a direction pin. The direction pin tells the motor drivers which direction they are going to be moving, and this is controlled by either a logic low or a logic high. And the step pin allows you to send a single pulse, and the single pulse going into the motor driver will make it go 1 single step. We are going full steps in this configuration because the full step pins are all left open, which allows them to be low, which puts both motor drivers into full step mode. And to make a move, all you do is change the analog stick position. Up increases the y-axis, down decreases the y-axis, left decreases the left axis, and right increases the x-axis. If you hold the C button, you are actually able to control it using the accelerometer inside the nunchuck. Left and right control the x-axis, forward and back control the y-axis. You can also do a combination of both of these to move diagonally.
For our project, our code was compiled using Kyle, but for simplicity, I'll explain the code with VS Code. So here's our main file. First, we initialize our clocks, and we have an UART initialized for debugging purposes. We initialize our I2C with our I2C file. And then we also initialize our Nunchuck by enabling the clock, making sure their alternate function, with the alternate function register being set to I2C mode. High speed, open drain, and pull up resistors are all set for the serial clock line and the serial data line. And then what we have is we initialize our stepper motors to initialize them as outputs for the X and Y step and direction pins. And then we come through and make sure that we have variables to store the data from the Nunchuck, as well as the codes to send to the Nunchuck when it first starts, and then also a delay. We send the data to the Nunchuck to wake it up and make sure we're talking to it. And then this is our array to store the data that comes from the Nunchuck, the X, the Y axis on the joystick, as well as the accelerometer. And then in our Nunchuck drive function, we have it where we send the data to wake it up, and then we read the data, and then we interpret this data and decode it by XORing it with hex 17, and then we read in the X value of the joystick, the Y value of the joystick, X of the accelerometer, Y of the accelerometer, the C button, and the Z button. And then if the C button's pressed, we read the data and move the Nunchuck with the X direction and move it with the Y direction. This data is then interpreted with our stepper command. If the joystick is in the left or the right, it'll step that motor with direction 0 or 1. And same thing with the accelerometer. And then the Y axis uses the same code. And that's our code.
Now, as with every project like this, we did run into a variety of mechanical issues. We originally wanted to keep costs lower by 3D printing all of our parts. However, we realized that because of the weight of the motors, we needed to have stronger parts, and also that the more complex threaded parts needed to be made with metal, because 3D printing those makes it so that they are not strong enough to fit into one another. So we decided to change to an M6 threaded rod and wooden dowels instead as our sliders and our threaded axis movers.
Another variety of issues we ran into are obviously with the programming. It took us a while to implement an I2C communication with the Nunchuck. Specifically, we had all the I2C written, but we couldn't figure out what values the Nunchuck was sending back. They were kind of like encrypted and kind of unreadable at first. Then we were able to find, looking around online and at the lecture slides, that we needed to change and XOR the data with hex 17, as well as adding hex 17 to each of the data bits. We were able to do that, and the Nunchuck came back fine. We were able to read the values as decimals, and it worked after that.
If we were to do this project again, I would say that we would upgrade our mechanical designs from, instead of threaded rods, to belts. The reason that we did not do that this time is because we were under time and funding constraints. And also we would create a better gearbox so that we could increase the speed of the stepper motors, because we noticed that in our current design it runs slower than would be ideal. And a way to speed that up without losing too much torque would be increasing the gear ratio.
Another thing we would change on the programming side would be to implement a PWM signal to increase the speed of the motors as well. With time constraints, we weren't able to make this happen, but we would implement that. As well, we would also want to implement interrupts so that the communication with I2C could happen at the same time or in a very, very organized and efficient fashion as the signals sent to the motors to tell them to move. Overall, we feel like our project was a huge success, and we are glad we were able to implement it.
We thank you for watching our video on our final project for ECU 3710.
We hope you have a good day.